Hi everybody. I'm going to go over solving the practice quiz right now. You'll see that up in red here is the question that we're really trying to solve by learning stoichiometry, which is how can we determine the amounts of chemicals in a reaction? In other words, if we're given some goal of some amount of chemical we want to make, how do we figure out how much we have to put in to get that? So the first analogy in this chapter is that balanced chemical equations are recipes, which is why we're starting right away with just recipes. Questions number 1 and 2 are about making a turkey sandwich with 2 pieces of bread and 3 pieces of turkey. And it's represented right in this problem by this equation. So here the 2 and the 3 refer to the number of pieces of bread and the number of pieces of turkey. And the BR2 TU3, they're subscripts here because they're bonded. We're pretending that the sandwich is a new bonded thing. And I guess you could pretend that the sandwich is bonded together. All right, so 2 pieces of bread, 3 pieces of turkey make 1, because there's no number in front of it, we assume a 1 turkey sandwich, which is that BR2 TU3 thing. All right, question number 1. If the deli has orders for 200 sandwiches, how many pieces of bread will we need? Well, we're going to do 200 of the sandwiches. We know that the formula of sandwiches, we always look to the equation for the formula. So that's the BR2TU3 formula. So I'm going to put BR2TU3 for sandwiches. All right, I'm going to do this in dimensional analysis. If you like the dumb way of doing stoichiometry, you can use that as well, but I'm just not going to do this during this video. All right, so we got that 200 of BR2TU3, and now I'm going to need a mole ratio. All right, the mole ratio is going to be the mole ratio of sandwiches to bread. Why mole ratio at this point? Well, we're in essentially what would be moles or particles. We haven't done a lot of problems with particles, but you could use 6.02 times 10 to the 23rd here. You don't have to. We can just pretend it's moles because remember the big idea from this chapter is that balanced chemical equations are recipes written in moles. So we'll just pretend that they're moles. So 200 moles of BR2TU3. And we're trying to solve out for bread. But the important thing is that sandwiches to bread, that particular mole ratio is going to be the sandwiches to the bread. So the mole ratio is 2Br to 1 BR2TU3. So it's going to be 2Br on the top because we want to go to bread, and 1 BR2TU3. That's the sandwiches on the bottom because we want to cancel that. So BR2TU3 cancels, and we do this out, and pretty much we're just going to multiply 200 times 2. And so we're going to get 400 breads. That makes sense. If you want to make 200 sandwiches, and each sandwich has 2 pieces of bread, you get 400 pieces of bread. This was just the dimensional analysis to show how you solve this out. All right. The important part here now is what's the mole ratio? Well, it's that thing. So you just need to rewrite that. 2Br and 1Br2TU3. So you got to write that. That's your mole ratio. All right. Or you could write it upside down, or you can write it 2Br equals 1Br2TU3. All right, so the mole ratio comes from the equation every single time. All right, we're going to move on to the next problem here. And this is number 3. This space in the middle here is just to do work if you want extra space. But the question is down here. I want to calculate how many grams. I'm going to analyze the problem. Many grams of iron. So we're going to solve for grams of iron. And it's going to be produced from 50,000 grams of Fe2O3. Well, this is a gram to gram problem. Gram to gram. And we know when we are using gram to gram problem, this is from the mole map that we use, that we need to go from grams to moles, and then moles to moles, and then moles back to grams. So we're going to use the molar mass, we're going to use the mole ratio, and then we're going to use the molar mass. Because we always use molar mass to get from grams to moles, and we always use mole ratio to get from moles to moles. Remember, this entire side here is all about iron, and this entire side here is always going to be about, oh, sorry, let me fix that. We're starting with iron oxide, so Fe2O3. This entire side's about iron oxide, and this entire side that we're trying to solve for is about iron, because that's what we're trying to solve for. All right, we're going to set this up like any stoichiometry problem. We're going to put our starting amount over 1, Fe2O3. Make sure you have a number, a unit in a formula, so it's got to be labeled well. Put it over 1. All right. And remember, we're going to use our molar mass, our mole ratio, and our molar mass. So this is the molar mass, mole ratio, and molar mass. All right, first molar mass, it's going to be about Fe2O3 because that's the thing that's labeled there in the formula. So 56, I look up on the periodic table, 56 times 2 plus, look up oxygen on the periodic table, it's 16 times 3. And I'm just writing the work up above here, but you don't actually write it there. When you write it, you're going to write it in the denominator, which is where I'm about to write the answer. So it's 160, and the unit of that is grams. Right. The special thing about molar masses is they're 1 mole. That's why we write 1 mole in the numerator, because 160 grams is a mole for iron oxide. Right. Grams cancels grams. Now, the point of the mole ratio is to cancel the Fe2O3. That's what we want to cancel here, the Fe2O3, and we want to get Fe in the end. So that's why we want to cancel the Fe2O3. So the mole ratio, we're going to look up in the equation, because mole ratios always come from the equation, and we see that 2 Fe2O3 and 4 Fe. We pick those two because those are the two things we care about. We don't care about carbon. We don't care about carbon dioxide, CO2. We just care about the Fe2O3 and the Fe. That's why that's going to be the mole ratio. All right, so we're going to put the 2 Fe2O3 on the bottom. Why 2? It's because it's 2 right there. And it's going to be 4 Fe. Why 4? Because 4 there. You don't need to simplify this thing. You just write it down like it shows right here. All right, that cancels the Fe2O3. And now, if we stopped right here, we'd be in moles Fe. Well, we don't want moles Fe, we want grams of Fe. That's what it asked us in the original problem. So we're going to go in, we need to use the molar mass again, molar mass, this time of Fe. And so when we do that, we're going to do 56 grams. That needs to go on the top this time, not in the denominator, because we want to go to grams and we want to cancel moles. So moles has to be in the denominator. So moles cancels moles, and now that's going to be grams Fe. So we got 50,000. I'm going to do the workout now. So 50,000 times 4, right there, times 56, and I get a number that's a really big number, 112,000,000, and grams Fe over, the denominator is 160 times 2, so 320. So let's do that thing again. Divide by 320 and solve for a final answer, which is going to be 35,000 grams Fe. That's a reasonable number because remember, we started out with something in the thousands, tens of thousands. So it seems pretty reasonable that we'd have something in the tens of thousands at the end. All right, that's our answer. All right, we're going to move on to number 4 now. All right, this problem, if we analyze it, it's moles of fluorine and 3 moles of krypton hexafluoride. All right, it tells us also that this problem's unbalanced. You remember the big idea in this chapter is that balanced chemical equations are recipes written in moles. They got to be balanced though. So if you look in this problem, there's 6 F's here and 2 F's there. So we're going to need to multiply that by 3. And that pretty much solves it. So you put a 1 there and a 1 there. You don't have to write 1, but it really means 1 if they're blank. All right. So we're going to set up our problem. We have our starting amount. It's 3 moles of krypton hexafluoride. I'm sorry, I should have written just moles there. So 3 moles krypton hexafluoride over 1. All right. By the way, krypton hexafluoride is a gas that they use sometimes to put out fires in places like libraries where you don't want to get the books wet. So if you have this kind of gas, it's a fluorinated gas, it will make sure that there's no oxygen for the fire, but also that you don't damage the books that you're trying to save. Anyway, we're going to solve out for krypton. So here we've got we got to do, well, we're starting with moles, and we're ending with moles. So this time, we don't need a molar mass. We just need mole ratio. We're just going from moles to moles. So since we're going just from moles to moles, we just need the mole ratio of 1 of these to 3 of these. So the 1 krypton hexafluoride goes on the bottom. That's from that. And the 3 fluorines go on the top. And so 9 moles of F2 is our answer. All right, we're going to move on to the next problem. All right, this time, starting with grams, going to liters of carbon dioxide. So this time, we're going to start with grams. We're going to go to moles. We're going to go to moles. And then we're going to end up in liters. So we're going to use the molar mass, the mole ratio, and then that 22.4 number, because that's the molar volume. All right, the balanced chemical equation is already there, so we're going to be able to get our mole ratio. So we're going to set it up to 16 grams of C5H12 over 1 times, we need to get the molar mass of C5H12, so we look on the periodic table, it's 12 times 5. That's the mass of carbon on the periodic table, times 5 the subscript, plus every time we switch an element, we add 1, that's the mass of hydrogen, times 12. So 12 times 5 plus 1 times 12 is 72. So 72 grams goes in the denominator. The denominator because we want to cancel moles. All right, now we want to use the mole ratio. It's the mole ratio of the two things that are in the problem. This thing and this thing. Those are the two things we care about. That's the mole ratio. So it's going to be 1 C5H12 and 5 CO2s. And then finally, at the end here, remember, we're not using molar mass. Don't add up 44 grams of carbon dioxide because we don't care about grams at the end. We care about liters. We're going to use 22.4 liters, and that's 1 mole. All right, if we're talking about liters again, we got to use the 22.4 number. So the math is going to be 216 times 5 times 22.4, and then the answer of that divided by 72. And I got 336 liters of CO2. So that's the answer to that problem. Number 6, we got grams of SO2 to grams of FeS2. So 64 grams of SO2. Remember, number unit formula. Number unit formula. You need all 3 of those things. All right. We're going to use our molar mass to cancel grams. We're going to use our mole ratio to get over into the new formula we want, which is FeS2, and then we got to use our molar mass again. So this pattern should be looking familiar to you right now. So 64 grams is what, if we look up on the periodic table, is 32 plus 16 times 2. That's 1 mole. All right, the mole ratio is 8 to 4. So we're going to do 8 SO2s. Oh, sorry, I'm putting it out in the wrong place. We've got to cancel the SO2. That's why it has to be at the bottom there. And then in the numerator, we're going to want our, what is it going to be? It's going to be 4FeS2. And then finally, we need our molar mass, 56 times 2 plus 32 times 2. It's 176 is our number of grams. We put that in the numerator because we want to cancel moles, and we want grams to be in the final answer. That's why it goes in the numerator. So the answer is going to be 64 times 4 times 176 divided by, if you do it all in one step, make sure to put parentheses around these, 64 times 8. So I'm putting parentheses in my calculator, and I got 88 grams FeS2. All right. This problem right here, number 7, is a limiting reactant problem. We know that because there's 2 starting amounts. So the first thing we got to do is figure out which one of those is actually the limiting reactant. We got to do our steps out. Remember, the steps are, if in doubt, mole it out. So we're going to do 2 grams because it's H2. So this is H2. And so we got 2.5 moles of H2. All right, we're also going to do our 72 grams of O2. And this time, O2's molar mass is 32 grams. So 72 divided by 32 is 2.25 moles of O2. All right, we're not done yet, though. We have to divide by the coefficient. All right, the coefficient of this is 2, the coefficient of this is 1, and so we get 1.25, and we get whatever 2.25 divided by 1 is, which is 2.25. All right, the lower number is this one, which means that H2 is the limiting reactant, and O2 is excess. So O2 and H2 go down here. All right, the only reason to do all this work was to figure out what was limiting and what was excess. We actually have to solve the problem now. So the problem we solve by using the limiting reactant, which is the 5.0 grams of H2, and putting that over 1. We got to use the molar mass to get to moles. We've got to use the mole ratio. Well, mole ratio this time is going to be grams of water is what we want to find. So we got to use 2 H2Os and 2 H2s on the top. And we're going to use, go to grams, so 18 grams is 1 mole. And so we're going to do that all out. 5 divided by 2 times 2 divided by 2 times 18, which is going to be 45 grams H2O. And then finally at the end, that's called the theoretical yield. The 45 grams, because that's how much we should make. But if we actually only make 12, remember we do actual divided by theoretical, and that's going to equal the percent yield. So it's going to be 12 divided by 45. So 27% yield.